Hello everybody, welcome to AP Calculus, Unit 1, Lesson Number 1. Introducing calculus can change occur at an instant. In this lesson we're going to talk about limits and kind of give you a basic introduction to the idea of what a limit is and talk about rates of change a little bit and things like that. Start right here with this first question for you. Stop and think for a second, and if you want to take a pause on the video when you do this, what does the word limit mean in the quote-unquote real world? Think about what the word limit means to you, not from a mathematical standpoint, but just purely from an English standpoint. And go ahead and pause and think about that for a few moments. All right. To me, when I think of a limit in the real world, I'm thinking of some kind of border or boundary that we can't exceed. Let me spell boundary right. Which leads us right into the next question. Where have you seen the word limit used or the idea of a limit? To me, you talk about people, know your limits. This is some kind of boundary that you can never break through. You're stuck there. It's where you're capped out. Or, another place we've heard the word limit, I'm sure, is, speed limits, which are, supposed to be boundaries that your speed doesn't exceed. Of course, nowadays it seems like there are more speed suggestions than speed limits. But you can probably think back through your life and think of other times where you've encountered the word limit and how that word applies in your particular individual context. Now, in mathematics, the limit is a different thing. It's not a boundary, or it's not something you strive for. It's actually a numerical value is a limit, or usually it's a numerical value. Sometimes limits don't exist, but usually it's a numerical value. And we've got our definition right here. It says that a limit refers to what value a function is approaching as the independent variable approaches a specific value. And this is a brand new concept for us, completely different from what we've done in any of our previous math courses or algebra courses or pre-calc or anything like that. In those courses, what we did was we found the value of a function at a specific value of the independent variable. If we have a function of x, and if x is equal to a particular value, then we substitute that value a into that function, and it gives us an output, a value y. Okay? In calculus, what we're going to talk about much more frequently than this idea is that if we have a function and we have a value that x is getting closer to, not that it's going to actually be, but that it's getting closer to, we're going to find the limit as y approaches that particular function value. So what is the value of the function going to get closer to as x gets closer to the value of a? All right, let's start with a first example to kind of work our way through the idea of a limit. Example 1 here. Given the function f of x equals 1/2 x cubed minus x minus 1, what is the rate of change around x equals 1? Okay, and up to this point in your life, whenever you've heard the phrase rate of change, you've always thought about the slope. The slope between 2 points represents the rate of change. Okay, so what we're going to do in this problem is we're going to try and estimate or find what the rate of change is around where x is equal to 1. So instead of really finding the slope through 2 points, we're going to try and kind of estimate what it is at that 1 point, at x equals 1. And we're going to do that by using the idea of the limit. So the first thing I'm going to do in order for us to do this is I'm going to pull up my calculator here, and I'm going to go ahead and graph f of x equals 1/2 x cubed minus x minus 1. And I'm going to use this to do all of these calculations along the way. So the first thing I'm going to do is I'm going to come out here and I'm going to ask my calculator to tell me what the value of y of 1 is at 1. That's going to be this f of 1 value right here. So I'm going to ask it what it is there, and that's -3/2. So I can go ahead and use -3/2 in all of my calculations. And then I'm going to use calculator shortcuts to calculate these slopes. The first slope I'm going to find is the slope between the points 1, f of 1 and 1.4, f of 1.4. And so in order to do that, I'm going to set this up, and I'm going to make this y1 of 1.4 minus y1 of 1, and we're going to divide that by 1.4 minus 1. And this is going to go ahead and calculate the approximate value of the slope between those 2 points, which is going to be 1.18. And I'm going to continue to move this x value closer and closer to 1 as we go through this process. So now I'm going to do the same calculations with 1.3. I can just go through here and edit on my calculator what I want it to do. And if you don't know how to do that on your model calculator, a lot of the models, if you hit the second enter, it'll bring up the last, I think it's second enter on most calculators, bring up the last thing you typed in, and then you can just go through and edit it instead of having to type all of that in again. All right, and then I do the same thing with 1.3, and so that's going to be 0.995. And I'm going to go ahead and do the same thing with 1.2. We get 0.82. Excuse me. And then I'm going to do the same thing with 1.1. And that gives us 0.655. And then I'm going to do the same thing with 1.01. So all I'm doing here is just using my calculator to continually find the slopes between the points, the point 1, f of 1, and another point that's getting closer and closer to that point 1, f of 1. Now we'll try 1.005. We get 0.507. 5125, and we'll try 1.001. We get 0.5015005. And we'll try this last one, 1.005. And what you should see as we look at this is you should be starting to notice, if you haven't started to notice already, what did I do? Oh, I forgot a 0. Whoop. And so this is 0.5007, 50125. And so now the question becomes, as this x value right here is getting closer and closer and closer to 1, what's happening with these y values here? What are they getting closer and closer and closer to? And that's going to be our estimation of the rate of change. Okay? So what does it look like that value is getting closer to? Well, it certainly looks to me like that value is getting closer and closer to 1/2 as x gets closer and closer to 1. And so that's going to be my answer to this last question here, that my estimate for the rate of change of this function around x equals 1 is that it's going to be pretty close to 1/2. All right, let's keep rolling here. Why did we have to use limits? Well, I mentioned at the beginning of that we're used to finding rates of change through 2 points, the rate, by finding the slope. And since the rate of change at a point, also known as the instantaneous rate of change, is being found at 1 point instead of 2, that can be a little troublesome. It says here, up until now we've used the average rate of change, which you see right here. Slope is f of b minus f of a all over b minus a. But now what we want to have happen is we want the rate of change at the instant where b is equal to a. If we put b in here instead of a, you notice we end up getting something that is, and I'm not going to use an equal sign, we end up getting something that is going to be approaching 0 over 0. And that's a big problem for us because it's going to cause us to divide by 0. So instead what we're going to do is we're going to try and find the value that m is approaching as b approaches a for this slope formula. And that's exactly what we did with our calculators there. The limit that we found at the end of the previous page, that's our instantaneous rate of change at x equals a, that 1/2 that we found at the end of that problem. Okay, now let's keep scrolling down here. There's a big list here. How can instantaneous rates of change be used? We just talked about how to find one by using this idea of approaching a value and finding the instantaneous rate of change at that point. We can use rates of change anytime we have something that we consider an interesting rate. Velocity, speed, acceleration, the flow of liquids and gases into and out of containers, rates in and out, cars coming from a car lot, oranges being placed on a display table in the grocery store. There's growth and decay, there's temperature, there's electrical current, there's chemical reactions, population, both the growth of the population and the density of the population are interesting rate ideas to cover. Marginal cost and marginal revenue from economics in order to predict our future cost. Thermal conduction from like a science idea. We look here, and this is certainly not a comprehensive list, but these are all possibly interesting rates where we could use the instantaneous rate of change in order to find them. And the last thing we have here at the bottom of this page, how can we best estimate the instantaneous rate of change of a function? Well, it depends on what we're looking at. If we're looking at a graph or we're looking at an equation, maybe we want to find a couple of points or a couple of values and build a table of values and then try and use what we think is going to give us the best estimate based off of that information. Okay? You know what, we're going to cut this video off here and we'll have a very short second video for this section where we go through examples 2 and 3 of this lesson. So please join me then for that video. All right, see you next time. Bye-bye.